Mhm. Well, hello, everybody. This is Scott Roberts, and with me somewhere is Jerry Hubbell. There he is. So, Jerry's
Yeah,
been a busy guy lately, uh,
yep.
we wanted to start a short series about what it's like to go through the Mark Slade Remote Observatory training experience. And Jerry's one of the educators there. And so I'll let you take it from here, Jerry.
All right. I've been trying to get my ducks in a row here so I can share different things on my desktop to walk you through this. I'm going to start out with going over the slide I put together, the basic training. You can call it a basic training. It was like a 2-session that we held back 2 years ago, I think, with our initial batch of astronomers for the Mark Slade Remote Observatory. And this is the first session's presentation I put together. Let me pull that up.
Okay.
Let's see.
Now, Jerry, I mean, before we even get started, you know,
Mhm.
you guys do some pretty advanced stuff at MSRO. Do you think that this is hard for a beginner to do?
I wouldn't say it's hard. It's because we step you through it, and we definitely don't want anybody to fail. That's not that type of training. This is training that we will work with you and introduce you to equipment, techniques, and things. You do have to have a certain mindset to learn these things, right? I mean, we do
Okay.
get into some detailed information that can have kind of a sharp learning curve if you're not familiar with the technology.
Mm-hmm.
If you're just a rank beginner, like maybe you're a student in high school, which we've had several people and students from high school and colleges work on them with us on the MSRO at the MSRO Observatory. But basically, we work with you to understand the observatory, how it's constructed, how it's configured, what equipment is in there, and that's the equipment side. That's kind of the technical side of it in terms of the equipment and the observatory itself. And then we got the observing side where we talk about how you create an observing program for whatever things you're interested in.
Okay.
There's a lot of different celestial objects, and there's a lot of different ways of looking at these celestial objects. So we'll work with you, but we introduce a lot of different topics, and I've talked about over the last several weeks about the basic techniques of astronomy, right? We're talking about astrometry and spectroscopy and photometry. Those are base techniques that every astronomer learns on how to do measurements in the sky.
Mm-hmm.
They're bedrock techniques basically. And then we take it from there and apply those techniques to very specific objects. And then we have, how do you tune these techniques for those objects? For like, there's a way to do minor planets versus a way to do variable stars. The equipment's the same. The techniques are very similar or substantially the same, but the way you analyze the data and the way you consider the data is what's different
I
depending on
see.
what object you're looking at, right? So you would expect a variable star light curve to be very different from an asteroid light curve, for example,
Mm-hmm.
or even an exoplanet light curve. So even though we're measuring light curves and the techniques are the same, understanding what it shows us is very different depending on the object. So that's the kind of difference that you'll run into.
I see. I see. And um, the how long does the training last?
Well, so we take it in levels. So you get a first shot of training. That's the introduction that goes you the overview of the equipment and creating your observing program, and then you get into more detail working with the equipment. You basically at the next level of detail, we get into doing not just classroom training and exercises, but also labs where you work on with the telescope directly to learn that piece. So you get an introduction at the first, and then you start focusing in on the different detailed operation of the telescopes, configuration if you're into the technical side of it, or if you're doing the observing program side of the training, then you're going to learn about the techniques to observe, how to set up the session to observe the objects, and then you get into, once you take the data, learning to do that, you get into the analysis side. So there's basically two tracks of training at the MSRO. One is the technical training track where you learn about the equipment and the configuration and how it all works. And then the other side is the observing track where you actually concentrate on what's up in the sky and learning about the objects in the universe and how
Mm-hmm.
to observe and take data and analyze the data, that type of thing.
I see. Very
Hmm.
cool.
Yep.
All right. Well, I'll let you, I guess, take a dive into, how people get started here. To be very honest with you, Jerry, I'm very interested in taking the course myself.
Oh, sure.
So, I think I'll talk to you after the show and we'll hook up.
We've
So
actually got Jeff Weiss. I don't know if he's in the audience, but
I
he's
don't
actually
know.
he
Let me
sent us
see
an
who is in the
email.
audience
Yeah.
today while while we're looking here. Let's see. We got Beatrice Hines. We've got Book Davies, Martin Eastburn. He said, so far so good in East Texas. Kyle Bannister is on, says hello. We've got Aaron Thompson. Yep.
Oh, Aaron's good. Yeah.
Hey, Aaron.
Yep.
We've got, I think I mentioned Book Davies. We got no, people are just chatting back and forth here. Tarek is on, and he is he's cooking food by himself and eating it.
Oh, well, that's what you do.
He says, join him. Okay. We'll have to have a cooking show, Tarek.
Yeah, right.
He says, is also searching for options for my setup, so I finish search and start imaging soon this year. Oh, very cool. And he's making pasta with chicken and white sauce and mushroom. Tarek, I'm a vegetarian, so we'll have to, I'll eat everything else except for the chicken. Let's see. And Senthil Kumar Nagapan saying, he says, thanks very much for the drift alignment session, Scott. Kind of curious if he actually tried it. He says, I need to try this week. Okay. And then we got Jim Zastron, and of course, Cameron Gillis. So he's listening in. And anyhow, so that's the chatting audience right now. And for all of you that aren't chatting, welcome. And if you have questions, feel free to ask us a question on the live chat, and we can go from there. All right.
So this is the first presentation you'll see as a student. It's session introduction to the MSRO facility, equipment operations and observing programs. Okay, and I'm not going to go through every slide here. This is just a talk about the training. So that's what this first session's about. We'll go, introduce you to the instructors, which is Myron and myself. Myron's the observatory director, and there we are right there with Station 1. You see the beautiful ES ED 165 up there that we use as our primary training facility. We do have 2 other stations that we can train on also that more than likely you'll be using for different things. So the training, this is meant to be a one-day session, basically, a full 8 hours, I would say. Probably not quite 8 hours, probably about 6 hours. You get an introduction to the facility and the equipment, and then you get an introduction to the observing program. So depending on which track you take, that'll help you decide, basically. Or you might want to do both tracks. Doesn't matter. They're both very interesting. So one of the things we do is we go over training objectives for whatever training you have, whether it's just introduction training or if you have more detailed training, you'll have a list of training objectives. And you'll also have quizzes and exercises to go through, especially with the lab type training. And then you'll have a test, okay, whether it be a practical test or a written test, you'll have that also. So for example, here's session 1's training objectives: to understand the history of the Mark Slade Remote Observatory, to appreciate the purpose and mission of the observatory. And that's kind of a key thing that we like to instill in our students, why we're a little bit different than a lot of other observatories in terms of commercial type observatories. To learn about the equipment used to help you understand how it contributes to the overall operation and performance of the observatory. So that's another important objective where, we don't have a piece of equipment in the observatory that's not used or not necessary, okay? Every piece of equipment that we mount, we want to make sure that it's there for a reason and it contributes to the overall performance of the observatory. So that's another interesting thing to understand. And then we talk about how the instruments and equipment and the analysis software allow you to gather and analyze the data to meet the goals of your observing program. So how does the observatory equipment and software and tools contribute to meeting your goals in the observing program? Okay, that's something you're going to understand.
Mhm.
And then how to operate, how the observatory operates, and how to control and operate the equipment. That's another goal to meet the needs of your observing. So this is a hands-on teaching observatory. It's not like most commercial systems where you submit an object to observe and it does all the work. It's all fully automated, which is necessary and to get the most use out of the observatory for people. And it's automated. You submit a schedule, you wait a couple days, and then you get data. You get a notice, email that your data is ready to download, and then you do your analysis yourself. That's typically how commercial services work. Ours is a little different, where we have an online, hands-on teaching where you actually operate the equipment directly, and I'll demonstrate that here in a few minutes, what that's like. So like I said, this first section is introduction to the facility and equipment. So we're going to talk about the history of the Mark Slade Remote Observatory, and then you get an introduction to the history. And I'm not going to go through every one of these slides. I'll just skip through here. So we talk about the history of the observatory. And then we talk about the facility and the equipment. So the facility is made up of a lot of different things. The building, the telescopes, the control system, the imaging instruments, the computer system and applications. We have network equipment and then power system equipment. So there's all these pieces, parts on the technical side that you'll learn about in detail. So for example, you see we got these different, these were concept diagrams I came up with
Mhm.
for the observatory. And then there's another drawing. And then you can see we go through the building of the observatory right here. I know I'm just going through this fast, but
You guys
so
built
you'll
that
go,
observatory pretty quickly, as I recall.
yeah, it was like a 2-week period
Yeah.
in December of 2015 that you can see we built it in Myron's garage right there, and there I am
Mhm. He likes
in the
building in the
show,
garage. Yeah.
right? It was
Mhm.
pretty cold at the time, but it worked pretty well. Um, so that was the first telescope we put in, was this 12-inch Meade LX200, which worked for a while. We talk about the equipment. So there's the 165 that we have in there now. So we go over, and then we go over the control system. So overall, this is the kind of interaction you'd have at the beginning. We'd have the remote training through Skype. And today we used to do Skype, and now we use Zoom. So more than likely, when we do sit down to do this training, you would
Mhm.
come into a Zoom session like we are right now, and the instructor would be sharing his desktop, just like I'm doing just right now, like we're all doing now, and we would go through the program.
So I'm going to throw a challenge out there. When I sign up for this, I'm going to see how many of you guys want to do it with me. So
That'd be cool. So let me see what else. Oh, here's the second half. So we have lunch, and then here's the I did that I duplicated this slide because we just go over what the introduction. So this is going to be the session 2, introduction to the observing programs. So again, we have some objectives, and then we have imaging the cosmos as the first first thing. Talk about that. Start to show, I don't know how many, there's quite a bit of text in each slide you see, but that's more the part. And then we got some pictures to show the different, and this is the stuff that we went through in the show a few weeks ago. Astrometry, photometry, and spectroscopy measurements. And this right here, this is a diagram I meant to show while we were talking. You see how we got the astrograph and then we got this overlay on top? That's kind of how you do, that's how you do a measurement, and you scale it. That's how you do the astrometry piece. You overlay stars on top of your image and you adjust it, and then you can calculate the scale of the image from that. That's kind of a neat diagram that I came up with for my book. So there it is right there.
Is it helpful to have read your book on science imaging, scientific imaging, before you start this?
Well, it can, but again, that's the textbook I would use for this. So when you sign up for the training, you get a copy of the textbook. There's two textbooks that we have. One is the scientific astrophotography textbook, which is more dealing with the equipment and the technology. And so you'll get that book if you go that track. If you go the observing track, then you get the other book, which is the Remote Observatories for Amateur Astronomers, which goes into your observing program, how to use commercial services, and also how to, what kind of projects you can do with the remote observatory.
And how much will the training cost?
So let me bring up the page.
Sorry, I'm jumping around a little bit.
Yeah, that's all right. Let me bring up the MSRO science page, and I'll go to the training section. So you can share that link. MSROscience.org is the website.
Yeah, I actually have a link in the posting to go straight to the application.
Okay. So the application is just basically saying I'm interested in the training.
Yeah.
And then I'll contact you and then I'll send you a link, and the link will go to the student login to MSR Science training page. Okay.
Okay.
And what this talks about is basically all the information to talk about, type V and C we use to access the remote observatory. We've got Groups IO training forum that I set up for discussion use. We've got the textbook. So this is the link that's.
Go ahead.
This is the link right here where you actually go and sign up and pay for the training. So I'll go to that in a minute. But this is one of the books that we use, and then the course syllabus, procedures. You'll get all these different materials along with the training. So let me go ahead and go to this. Did you have a question, Scott?
Yeah. Let's see. Jeff Wise he said he's waiting to hear back from you, but
yeah. I'm sorry, Jeff, that I hadn't.
And Beatrice are kind of interested in taking this class with me. So, but we'll have to figure out the timing on it as well. I think Tarek's I think he's in the UAE. So, is the book a downloadable digital version as well?
Also, when you sign up and pay for the course, you'll get an electronic copy of the book along with that course, but you can also purchase a hard copy. And so if you go to this page, if you contact me, I'll send you the link to go to this page, and then you can look and get the more details about the books, which is all this text here. And I give basically my cost for the book, for each of the books. And then the training is several hours. It's quite a bit of time. So for example, the observer training is $800. The technical training is $800. The introduction course is $150. If you want a 3-hour block of time for training, it's $200. Basically, that's outside the normal, outside of this training. You get some observing time on the observatory with the technical or the observer training, but if you want extra 3-hour blocks of training, it's $200 basically. Now, we're a nonprofit. I want to explain the pricing here a little bit. We're a nonprofit organization. There's two ways that we make money. One is that we take donations, okay, which is truly a donation. It's a tax deductible donation that you get credit for. Now, if you want to, let's say you want to donate. Let's say you want to donate, but you want training. It's not really a donation. It's a quid pro quo is what it's called. So you're paying for the training and you're getting something for it. You can't count that as a donation. You can't get a tax deduction for that. So that's the difference between paying for the training and what we, and in order to be a valid nonprofit organization, is we are required to charge somewhat market prices for our training and our facility. And we've really made it inexpensive, to tell you the truth. It's really not that expensive to have full-time with the observatory or with an instructor, one-on-one in the observatory with us, and the time on the scope. It's kind of like when you go learn to fly a plane, right? You pay the instructor and you pay for the equipment, renting the equipment, that type of thing. So that's kind of the same thing we're doing here in the level of equipment that we have. We think we're pricing it very fairly. Now, there's some wiggle room and stuff. We'll work with you on a budget or whatever you need to do to obtain the training. But again, it's just like buying equipment. You're not just buying equipment when you purchase your own equipment. You're buying an opportunity to increase your own personal skills and knowledge.
Sure.
So it's an investment in yourself more than
Yep.
anything, right? So that's kind of the way I would look at that.
Right. Well, $800 is like one night of heavy drinking with your friends.
Yeah, right. Exactly. Well, and you get
Not that I've ever done that. Okay.
right. I've got another document I put together. I have to find it. Trying to think how many hours. So the classroom training is probably, it's a week's worth of training, maybe. We get into those levels of detail. We go through the books are the textbook for it. So they'll be reading assignments, homework, classroom training, and quizzes and testing. All right, and you'll get our certification. Now we're not have to be careful because we're not an accredited training facility in terms of like a college course or anything like that, or college credit. All right, this is a private, we're a private training organization. You get certified for use on our equipment and for your own personal equipment, how to operate and use and actually build your own equipment at some level, or integrate your own equipment into your observatory. So that's the kind of training we offer. But yeah, that's the meat of it. That's the meat of how you.
Some people here are, in different parts of the world, and we may not all be able to plan on getting together all at once, but it looks like there's some sort of level, of, financial ability to get in and do some training. And it seems like a lot of nonprofits, that you do work with people at different financial abilities. So that's cool.
Now, one thing I do have to say is everybody that purchases time and also purchases training, that money, since we're a nonprofit, that goes towards the direct support of the equipment in the observatory. None of the staff, we don't take a salary,
You
so we
guys
don't
don't
get
get
paid.
paid.
No, we don't
Right.
get paid for this at all.
Right.
Because we don't have the cash flow yet to really generate that. Now, what we do is a portion of this training, if it's paid, the instructors do get an hourly rate for that.
Mm-hmm.
Like Myron would get some, if whatever training he was due, he would get personally, because it's being paid directly as part of the facility. So part of it goes towards the astronomer's time for the instructor, astronomer's time. And then the other portion goes towards upkeep and purchase of equipment and maintaining
Sure.
the equipment in the observatory.
Right.
That's what we use and then also you can apply for a grant. So we haven't built up our funds enough to really grant time, but we do grant free time because we all have personal time that's available on the telescopes for us to use
I see.
as employees of the company. So like Myron will grant some of his time and sit and train somebody gratis, So if you have a need, if you have a student and you don't have the ability to pay for the training directly, then you can request a grant of time with an instructor, and we'll consider that. And we do a lot of that actually.
That's cool. That's cool. Well, it's certainly a worthwhile thing to support for sure. So, yeah, because you guys have done some amazing stuff. And the other thing I will say, I mean, I was on I was part of a committee with the American Astronomical Society. Unfortunately, was not able to attend all the meetings, but we did. What we did end up with is we formulated the different aspects of how the American Astronomical Society, which is an organization, is designed and formed for professional astronomers who are doing research. This is, if you're a professional astronomer, you definitely belong to the AAS, but they want to expand out to amateur astronomers. And we've talked about this before. They need amateur astronomers for ongoing observations of discoveries, or maybe it's not yet a discovery, it's a candidate, those kinds of things. So Jerry's been involved with the test team, for example. That's the orbiting observatory that is watching for exoplanets. And on one of these shows that we did a live transit of an exoplanet. So that was that was pretty remarkable.
Yeah.
We were able to pull that off on a live program. But the thing is that I've been involved in amateur astronomy since 1980. Where I would call it serious amateur astronomy. And I've dabbled in doing some pro-am stuff, but I've never really, been part of a team, that does ongoing types of things, and that's what they do at MSRO.
Yeah.
Okay,
right.
so I think this would be a great experience to learn more of these techniques. You can learn them with the MSRO team. And then you would apply those techniques that you learned on your own equipment, and then you would join up with the American Astronomical Society. It costs like $50 a year or something like that, and then you would have the opportunity to work with professional astronomers on pro-am projects. But you're not just somebody that's totally green, right? You would have already trained at MSRO. You would know how to do light curves. You'd know how to do, maybe you know how to take spectra.
You can speak the terminology. You understand what
you're not
talking about.
Go in there like a deer, in the headlights. You're going to know. You're going to know how to do this. And but just like when most of us learned amateur astronomy just to learn the constellations, just to learn how to switch that eyepiece for that eyepiece, or how to do astrophotography. We all had to have a learning curve. For most of us, we had someone that took us under their wing, and that's what MSRO is all about. So you'll be working with good equipment.
Yeah, let me bring up the observatory real quick.
Sure.
Now this is the screen you get before you log in. It's just like a regular old Windows desktop. So I'm gonna click on the login here just to show you what it's like when we start a session.
Mm-hmm. So this is the MSRO computer.
Yep, yep. And there, as you
Here it
see,
is.
it comes up with our fancy. This is just a concept of a desktop that I came up with that has a lot of reference material on the screen. This is basically its static graphic with all the icons arranged a
Yeah, I like
specific
that.
way. So one of the things I want to demonstrate the type of training that we get with on the technical side is kind of what I want to demonstrate how one of the programs works that are part of that's part of the system. It's called NMEA time. It's our GPS time reference. And so you can see up here, I've got this universal clock up on the upper right-hand corner that's driven off the PC clock. Now the PC clock is maintained via this program and our GPS receiver, like I talked about. Let's see if I can get it to pop up here. I've talked about this in other shows, but this is an excellent program that we use to keep track, to get very accurate time off of our GPS receiver. And it's good to, you can see here, it's less than 1 millisecond off right now.
Jeez.
So it's like a laboratory clock. It's really
Yeah.
kind of overkill,
Yeah.
but again, it's neat to have it like that. Then you don't have no question about your
Yeah, no question that
timestamps.
it's really accurate.
Yeah, right. So one of the neat things about this program is it gives you this status page that shows you where all the satellites are that you're tracking at the time that you're not are receiving signals from, I should say, and then gives you a very precise latitude, longitude, altitude above sea level, and then it shows you how many satellites, 8 out of 12 that are being used. The next thing, to keep that very precise time, it's got this control algorithm. Okay, and it shows you how the time drifts over, how the time value drifts over time, I guess,
Mm-hmm.
as you go along, and you can see it's correcting itself back to the zero, as
Wow.
close to zero as it can get. Um,
What is that
uh,
drift? That's not even, it's a millisecond, right? I mean,
so yeah,
or is that 5 milliseconds?
you'd have to zoom in. So this is 5, a clock counter. So I'm not
Okay.
sure exactly what the scale is for the clock counter.
Okay.
It's a few it's like that's probably like you said, 1 millisecond or something,
Mm-hmm.
because
Oh, right.
we know the variance is less than a millisecond right now. So you can see that that would be probably around a millisecond or so,
Yeah,
I would expect.
it's crazy. Yeah.
Um,
Okay.
so this continuously updates the PC clock or keeps it in line. It kind of prods it when when it drifts out. It comes prods it back into line. Um, I don't know if you can see the text here, but this is what the raw
Yeah.
data coming from the satellite looks like. It's just a bunch of text or strings of information that gets processed by the program.
That's cool.
That's an that's a that's an example of a piece of software that we have in the observatory that helps us meet our goals. And the primary goal for the clock is to time different phenomena that go on. Like one is for asteroid measurement, position measurements. You need to get the position down to a certain precision, and then also you need the time to within 1 second when you do the measurement.
Mm-hmm.
Now we do 100 times better than that, which is good. Um, the more precise you can be, the better off. And
Sure.
this is a pretty inexpensive program. I don't want to get into selling the program, but again, one of the other things we would talk about, I don't know what this is, start control loop log. So you can do logging. We've got configuration settings here. So set up the communications. You can see this uses comp. I don't know if you can read that or not. It's COM port 2 and it talks at 4800
Two,
baud.
yep.
So
Says
these are the
two
types
blocks.
of things you would write
Yeah.
down in your notes when you're taking the class. I'm, talking about this program. These are the settings. This is how you do it. What are this? We have the position format. So there's different ways to set the position. I'll go back and look at it. So right now I've got it in decimal.
Mm-hmm.
Oops, decimal degrees. I'm going to change it to degrees, minutes, seconds. And that's on this GPS status display. So now you can see the latitude and longitude are degrees, minutes, and seconds of position.
Mm-hmm.
And you can see how precise the position is. It's to
Yeah.
3 decimal places,
Jeez.
which is crazy.
Right.
It's within 5 feet
5 feet.
on the Earth's surface.
That's pretty accurate.
I
It's pretty
would
accurate.
say it's
So
precise. Yeah,
I'll,
yeah,
I'll admit to you, Jerry, I've been to a few professional observatories. Um, I mean, if we're not talking about the largest observatories, I mean, they're very advanced,
yeah,
but
yeah.
if you're talking about, meter class or,
Yeah, the
you know,
normal
yeah,
teaching
your normal
university
pedestrian
observatory. Yeah,
research observatory,
yeah.
you guys have all the software, all the tools, the same tools,
Oh
uh,
yeah,
in the way that they are functioning, okay, as these other observatories. So they'll make you, if you volunteer, I've talked about this before too, if you're an amateur astronomer, and you know something about, your way around an observatory and you know your way around doing science, you can often volunteer to work at an observatory.
right.
A lot of research observatories, they're running on a shoestring anyway, so they need volunteers. But they don't want just anybody in there. If
No,
you don't know, you don't know what you're doing, and it's going to take them more time than it's worth, okay, to get you up to speed, um, then they may not choose you as one of the volunteer
right.
people. But if you
That's
do
one
know,
thing. The technical track really gets you involved with learning about all the pieces of equipment in the scientific
yeah,
astrophotography book. I go over all the different equipment that you'll find in pretty much every observatory.
right,
Now we use commercial off-the-shelf components in our observatory. A lot of universities have departments, instrument departments, and other departments that develop specific instruments and different, self-produced. I guess they have
yeah, probably the
machine
students wrote
shops and other thing where they create
programs,
their
and
own. They
yeah,
create their own programs. Yeah, that's the other thing. They write
but
their own
it's doing
programs.
this,
It's the
right?
same stuff, right?
Yeah,
It's their own custom version of a commercial off-the-shelf system, basically.
right. Yeah, because it costs them
Uh,
less to do that.
right. Well, they're training scientists, they're training engineers, and they're building and designing these things. And that's
True,
how it all got started. So
true.
we actually do develop some instrumentation at the MSRO. We've done some fairly advanced work in that regard. So you do have an opportunity to get into that level of work at the MSRO, where you can develop. And the exoplanet work specifically, I helped develop techniques to use commercial off-the-shelf equipment to do the high precision exoplanet measurements that we need to do the on the test follow-up mission.
Hmm.
And this is off-the-shelf equipment that's fairly new. It's only 2 or 3 years old, that was pioneered at a couple of universities. And that's where I learned about it. So, and we apply it at our small telescope system.
Very cool.
So, that's the NMEA time. That's an overview of how it works. Let me see what the about screen is. So basically, available. I'll go over, basically this is the program. You would learn about this. You could download it yourself to try out. And it works great. And it's got a token. What does it cost? $20.
Yeah.
It's $20 for a laboratory level timekeeper on your
Yeah, that's what a cup of coffee at Starbucks costs now, I
right. So
think.
this is
Yeah.
something, 20, 30 years ago, they would have paid thousands of dollars for.
Right. That's right.
And it's available to us basically for free.
For free, almost.
So that's kind of an example of how I would go over some equipment in
Okay.
the observatory.
Okay. Well, that's a good start, Jerry. So I will apply, and for those of you who are interested in doing it with me as a group, that would be great. I will probably start with one of the beginning type of courses myself, and then
So we do offer the
there's-
introductory course, which is that 1-day course, I
yeah,
think for $150. It includes the
done.
training, and then it also includes some time on the observatory as a group.
Does it guarantee me like a discovery that I can get my name put on?
It's like winning the lottery. If we happen to pick something to observe, it's hard to say.
Hard to say. That's right.
Yeah.
Okay. Well, I'll do it even if I don't get a discovery. How
Yeah.
about
No,
that?
but you'll get lots of personal discoveries.
That's right. That's right. Well, that's cool. So anyhow, we will we'll follow up with this in the next few programs. For those of you that are watching, you can get in touch with me directly if you wanted to ask me questions about getting started with the MSRO or whatever, or you can reach out to Jerry as well. But I know Jeff Wise has already sent you an inquiry, so
Yep. I'm getting ready to respond back to him here in a little bit.
yeah. So that's that. So today, I forgot to say at the beginning of the show, today is John Dobson's birthday. He was born in, I think, 1915, and in Beijing, China. He led a fascinating life. And the Global Star Party tonight, our 62nd Global Star Party, is the celebration of his birthday. I asked Donna Smith, who is someone I know from the Sidewalk Astronomers, and if you don't know who the Sidewalk Astronomers were or are, this is the group that John Dobson started in San Francisco. They used to be called the San Francisco Sidewalk Astronomers, but I think they've kind of expanded all over the world. And this is a great group of people. We're going to have on the program lots of people that knew John Dobson, had experiences with John Dobson, have stories of telescope building, his humor, his philosophy on astronomy. And why is John Dobson so, such a big deal? Well, he devoted his entire life, I mean, really his whole life, his adult life anyways, towards, teaching other people how to enjoy the night sky. He starts off by showing people how to make a very inexpensive telescope, the Dobsonian telescope. He didn't call it a Dobsonian, didn't like the name Dobsonium, but that's the name that stuck. And so he always kind of teased himself over that. But I haven't seen any other program or anything where people are celebrating his birthday. And I thought, wow, for someone that gave so much to us as amateur astronomers, definitely deserves some recognition in that regard. And so watch tonight. We're going to be on at 7:00 Central, 5:00 Pacific. And Donna has I think 15 speakers, something like that. So it's going to go on pretty late. So hope you join us. A lot of our regular people that are on the program will not be on, simply because there's so many other new people coming on. But it's going to be fun, and I think that you're going to learn a lot about the man that really turned on a lot of people to the skies. So,
Cool. That'd be very nice
yeah,
to watch.
yeah, that's right. And so, and what else? Other news. Tomorrow, you're going to see a press release come out. Explore Scientific is now the official distributor for Vixen Optics. Vixen is a Japanese telescope manufacturer, optics maker, 72 years old. They've been around for a long time. We've been engaged in negotiations to be a distributor for quite some time now. And so I'm proud and happy to say that we are the official distributor for the Americas. So all the way down from Canada down to the tip of South America. So it's great product. I started selling Vixen when I was at Oceanside Photo and Telescope back in the 1980s. And I always thought the product line was very high quality. They also have a number of firsts in their repertoire of product innovations. Probably most notable is the GOTO system. Amateur astronomers enjoyed Vixen telescopes and their sky sensor product, which was the very first commercially available GOTO system. There were guys that were making homemade GOTO systems and that, like that. But if you wanted to go buy one, you had to go to Vixen to get it. And so that's something that I think that you'll find interesting about the product line. The optics are excellent, so we'll be getting into their product line probably this October, November, I would imagine, by that time. But the press release will go out tomorrow, and you're the first to know. Okay, so outside of the company. That's right. And Cameron Gillis is saying Vixen dovetail standard. That's true. They have they made a lot of innovations. Vixen has been often copied in the telescope industry. And
they set the standard for Exos 2 style mounts, right? With the Great Polaris mount or something.
Absolutely. Yeah. So what happened is back in the 1980s, you might see something called the Vixen Polaris mount, and then they had something called the Super Polaris mount. And they have had products that have a twist on the word Polaris, like the Polari equatorial tracking head and stuff like that. So it's they are the #1 brand of telescopes in Japan, and everybody knows how picky Japanese amateur astronomers are. So the quality is going to be good. I'm really actually very happy that we're going to be distributing the line. So, and other news. I'm sure there's some other things I'm going to talk about later. Maybe later in the coming weeks, we've got some new products that we're working on that maybe I can give you guys some sneak peeks into. And there's always something new, something else happening, something to talk about. So
there'll be something to talk about soon. Yes.
All right.
People will start asking about it when they find out.
That's true. So yeah, keep it a secret, folks. Don't tell anyone.
Yeah, don't tell anybody.
All right. You guys take care, and we'll see you in a couple of hours. What is it? 5 o'clock now. So 7 o'clock. Actually, we start broadcasting before 7, but yeah, watch the 60-second Global Star Party. Help us celebrate John Dobson's birthday, and we'll see you in a little bit.
When considering the possibility of life beyond Earth, we look for 3 main ingredients. The first one is key elements such as carbon, hydrogen, oxygen, and sulfur. The second is a source of energy. And the third, and perhaps most important, is the existence of liquid water.
Water is a necessary solvent in all chemical reactions that have to do with life. Energy is required to drive these chemical reactions, and organic matter is the material from which all life that we know of is made.
Life as we know it requires liquid water. Scientists believe that life on Earth started in our oceans. Now, through our exploration of the solar system, we've realized that the moons around the giant planets have the right conditions, that there could be liquid water underneath their surfaces. And so that really sort of expands our whole concept of where you could have a habitat, where we might find life.
Water is fairly common in the universe. We've seen traces of water in large molecular clouds between stars. We've seen traces of water in protoplanetary disks. We've also seen traces of water as water vapor in the atmospheres of giant planets around other stars. And we know that water is in the atmospheres and interiors of our solar system's giant planets. So we know that water is ubiquitous throughout the universe. As far as liquid water, that's a little less common. Earth is the only planet in the solar system where we see liquid water at our surface. Moons such as Enceladus and Europa may have liquid water beneath layers of ice.
We're really expanding our understanding of what makes a place habitable. Instead of just looking for an Earth-like terrestrial planet that's a very specific distance from its star, we're learning that there can be hidden habitats that are underneath icy layers, and they can be a lot further out from the sun.
So we believe icy moons in the solar system actually harbor kilometers-thick oceans underneath their icy surfaces. These icy moons and their subsurface oceans may be some of the best places to search for life elsewhere in our solar system.
Enceladus is one of Saturn's many moons, and it's a very small moon that people tend to kind of ignore because it's so small, about 500 kilometers in diameter. But decades ago, in the 1980s, from ground-based observing, we found out that the location of Enceladus relative to Saturn happened to coincide nicely with Saturn's E-ring. And so we were thinking that Enceladus had something to do with the E-ring particulates, the icy material, but we weren't sure. What we later find from Cassini was that we directly determined that there are indeed plumes jetting out of the south polar region from cracks in the south pole of Enceladus in the crust. And it's dominantly water-rich material, just jetting out into space. And so the way we saw it, Cassini happened to be located where Enceladus was backlit from the sun. And so you saw this curtain of beautiful diffuse material jetting out of the south polar region. Quite breathtaking, actually. Even more, we were able to use the different complements of instruments on board Cassini to go after the chemical composition of the plumes. And that's where things got really interesting. So number one, that's because of liquid water. There's definitely a liquid water reservoir. It's subsurface below the icy crust, but that is there. Number two, the chemical composition of the plumes told us that there's a lot of organics, things that make up amino acid and things on life that are very interesting. And number three, what we were really looking for is a source of energy. On Enceladus, photons from the sun aren't going to work because you can't penetrate the tens of kilometers of icy crust to get down to where the liquid water reservoir is. But what Enceladus does have is hydrothermal vents. It's very hot into liquid water. That has a lot of analogies with the ocean floor, where we have a form of releasing chemical energy via something called serpentinization. And so we think that Enceladus might have that potential to have an energy source being chemical, not sunlight. And so you put all that together, and Enceladus has all the ingredients, or most of what we need, for life. That makes it a very astrobiologically interesting object to study.
Europa is one of the largest moons of Jupiter, and we believe that Europa has a subsurface ocean tens to hundreds of kilometers thick. And so this ocean may be one of the best places to search for life in the solar system.
There's been 3 space missions that have provided evidence for Europa harboring liquid water. The first one is Voyager in the late 70s. The second one is the Galileo mission in the late 90s. And most recently, Hubbell, which detected plume-like emission from hydrogen and oxygen, which is closely related to the existence of water beneath its surface.
These plumes may be directly ejected through cracks in the surface of the moon, and therefore what we're seeing in water vapor plumes is the actual ocean water from the subsurface of the moon.
As these plume particles are ejected to space, solar radiation is going to excite these water particles, creating vibrational modes. Now, these vibrational modes are signatures that can be detected at infrared wavelengths by the Keck Observatory. So we observed Europa on 17 days. What we found is that the majority of observations have no presence of water. However, on one of those days, we detected water. We detected H2O. In the past, Hubbell provided indirect measurements of water by detecting hydrogen and oxygen. But now we have directly detected water for the first time.
Both the Webb telescope and the Europa Clipper mission will give us a much more detailed picture of the surface of Europa, its cracks and crevices, detailed pictures of the water vapor, as well as other molecules that may also be emanating from the subsurface of Europa. So both of these missions will give us a great picture of whether Europa is truly habitable.
Titan is a moon of Saturn. It's the second largest moon in the solar system, and it is about 2 times larger than Earth's moon and actually bigger than the planet Mercury. And Titan is also interesting. It's the only moon in our solar system with an atmosphere. It's surrounded by sort of an envelope of gaseous nitrogen, just like our own Earth is. Titan was first discovered by telescope observation back in the mid-1600s. The first spacecraft observations were made of Titan during flybys through the outer solar system. That was in the late 70s and in the 80s. But we really were able to explore Titan in depth with the Cassini-Huygens mission. The Huygens probe was dropped into the atmosphere of Titan, and it made measurements of chemistry, and it took images as it fell to the surface. And that was back in 2005. And since then, the Cassini orbiter made over 100 close flybys of Titan.
Cassini, in its design with the different instruments, we purposely were picking instruments that could go into longer wavelengths into the infrared so we could really understand the moon. We were able to basically peel back the layers of Titan to really see what was below, and it was remarkable, very Earth-like.
The landscape is similar to Earth's in many, many ways, but with a little bit of a twist. So on Titan, you can find dunes, you find lakes, there are river channels. The atmosphere is very dense, and you can get clouds and smog, and you even get rain.
We saw winds, we saw seasons, and one really important thing we saw was liquids pooling in the polar regions on the surface, a lot of it.
But because Titan is so cold, those features are all made of very exotic materials compared to what we would find on Earth. So the lakes and the rain are made of liquid methane. The crust that forms the surface of Titan is actually water ice, but it's so cold that it's as hard as rock. And in the atmosphere, we get this organic chemistry that forms large organic molecules and particulates. They fall down to the surface and then behave like dust or like sand does.
So it makes us want to go back to really understand the complex organic environment of that surface and what it means for either past life or maybe future life.
Dragonfly is a mission that was just selected by NASA to fly to Titan and arrive in the mid-2030s. Dragonfly is going to make a whole bunch of measurements to help us understand the environment on Titan and its potential for habitability. We'll be taking measurements of the atmosphere. That includes things like pressure, temperature, winds. We'll probe the surface to try to understand what materials the surface is made out of. We'll also be drilling into the surface to look for the types of organic molecules that are present and to try to see if we can find any examples of compounds that mimic the types of building blocks we know we need for life on Earth. We don't really know how life started on Earth. We don't exactly know what the chemical environment of Earth was like before life started. So with Titan, we have this really unique opportunity. There are times in Titan's past where there could be liquid water on the surface. Impact craters can generate impact melt, and there's a potential for possible cryovolcanism to erupt some liquid water onto the surface. And so we know that there's a rich organic chemistry going on in the atmosphere. We know that's depositing to the surface. If there were times where those organics and the liquid water environments were mixing, then there may be some really interesting chemistry taking place. When you have these processes operating for hundreds of millions of years, how far can they get you down that path of chemical complexity? And can we see reactions and molecules that start to look something like what we think of as essential elements for our biochemistry for life on Earth?
in the future, looking forward as opposed to looking back and thinking about Titan as a chemical laboratory for the prebiotic Earth, I like to look forward thinking about what's going to happen when the sun evolves and warms up and the habitable zone actually moves out to where Titan is. And it will. You have all the organics, you're going to have a source of energy. All we have to do is melt the frozen water, and we're going to have a pool of organics just embedded in liquid. Titan might actually have a chance at that point to harbor life.
So when we think about ocean worlds, it's good to compare them to what we know about Earth. In total proportion, Earth is about 0.1% water. An ocean world is a body that has, in proportion, about 10 times more water than Earth does. And when we think of the TRAPPIST planets, those planets have about 50 times more water in proportion to what Earth does. Ocean worlds do appear to be common in our galaxy. As far back as the early 2000s, we had astronomers, some of them still here at NASA Goddard, that suggested that we would have ocean worlds orbiting low-mass stars. Recently, we've looked at about 52 exoplanets, and these are low-mass exoplanets. And what we found is, of these 52 planets, 1 out of every 4 may be an ocean planet. And when it comes to these ocean planets, over half of them may be ice-covered ocean worlds. And so Enceladus and Europa may serve as small-scale analogs of these planets.
So there are a number of different ways to search for life on planets around other stars, but the key method is the study of the atmospheres. We can search for signs of life, biosignatures we call them, things like oxygen, water vapor, carbon dioxide, even more unusual biosignatures, things like chlorofluorocarbons or other things that are only produced by intelligent life. By looking for these key constituents of planetary atmospheres that signal life, we can discover life forms on other planets that we can never actually visit in our lifetime. So this is very analogous to how we study the atmospheres of moons and planets in our own solar system, and really makes the connection between studying the plumes of Europa and the atmospheres of planets around other stars.
What I would like to see is the definition of a habitable zone expanded. We don't want to keep thinking too narrowed about liquid on the surface, but broaden the scope and really try to embrace other worlds that might seem too far from the host star and frozen out when they really aren't frozen at all. At great depths, they harbor a warm, hydrothermal-driven, liquid water environment.
All right, Scott, I'll talk to you later. Talk to you later, Scott.